So, welcome to Civil IQ. Today we are going to discuss the fluid kinematics. This is continuity equation. So, continuity equation generally it is based on conservation of mass principle. Okay. So, this continuity equation is based upon the principle of conservation of mass. So, what does it mean? It means whatever the mass will be inflow in a fixed region, it should be equal to the mass outflow. Means the mass cannot be created nor be destroyed. So if you understand this equation, so this is the basic equation. So this is the basic conservation of mass equation. By using this equation, we can derive the continuity equation. So this m dot in means the rate of mass in minus rate of mass out will be equal to rate of mass stored. So if you take a pipe flow example, so suppose this is one pipe in which the water is flowing. Suppose this is my m dot in, the rate of mass is flowing in, and suppose this is my rate of mass is flowing. Suppose this is my rate of mass will be out. So I can write down basic conservation of mass principle. So this rate of mass in of this liquid water minus this rate of mass out of this water will be equal to whatever the mass is stored. If some mass is flowing, if some mass is out, if something will left, that will be stored in the system. Okay, that is the basic conservation of mass. Okay, so this is the equation by which you can derive. So now if you choose section, so this is section 1, so this is section x and x, so this is section xx, and this is section yy, so this is section yy, and in between this section if you choose the small part. Now if you zoom this one, this is the basic part on we will study this part. So this is the rate of mass flowing in this direction, x direction. This is m dot x. Suppose this one my is dx, and this is my dz, and this is my dy. Okay, and suppose this is my x axis, and this is my y axis, and this is my z axis. Okay, so there is some mass will be out of this system, that is m dot x plus this is dm dot x by dx into dx. Similarly, there is some mass is flowing in y direction, and there is some mass is out in y direction, that is m dot y plus this is dm dot y by dy into this is dy. Similarly, some mass is flowing in z direction, this is m dot z, and there is some out of this system, that is called m dot z plus dm dot z divided by dz into dz. This is my positive x, y direction. Now you'll understand this one. The mass flow rate means what is the mass is flowing per second. So this is m dot, this is the mass flow rate, can be defined as rho into q. So rho is the density of the fluid which is flowing in the system, and q is the discharge. So q is called discharge of the liquid. So this is discharge of the liquid. So if you make this one, this is q, density is kg per meter cube, and this is meter cube per second. So this is coming out to be kg per second. This is a mass flow rate. What is the mass is flowing per second? That is called mass flow rate. So this q is called discharge, or this is called volumetric flow rate. Volumetric, this is flow rate. Now what is the volume of the fluid is flowing per second? So the A is the cross-sectional area of the pipe or the container in which the water is flowing or liquid is flowing, and B is the velocity of the flow, velocity of the liquid. So if you do this, this is coming out to be meter cube per second. This is what is the volume of the liquid which is flowing per second. So if you rewrite this mass flow rate, if you put this q here, if you put the q here in this, so the mass flow rate is coming out to be density of the fluid into cross-sectional area of the pipe into the velocity of the flow. So this is the formula you have to remember. Mass flow rate equal to rho into A into B. The volumetric flow rate will be equal to A into B. So now we will derive the continuity equation from this one. So the mass of the liquid which is entering into the system. Suppose this one is m dot x, this is my x direction. Okay, so some mass will be out of the system, that is m dot x plus this is dm dot x by dx into dx. So mass is flowing in y direction, this is m dot y, and some mass is flowing out of the system in y direction, this is dm dot y by dy into dy. Some mass is flowing into this system in z direction, that is m dot z, and there is some out of the system, that is m dot z plus dm dot z by dz into dz. So now you will use the, suppose this is my dx, this is my dz, this is my dy. Now we will use our basic continuity equation, by conservation of mass equation, to derive this one. So our conservation of mass equation is m dot in minus m dot out will be equal to rate of mass stored in the system. This is the basic equation from which we will derive our continuity equation. So now we have to find, this is left part, and first we find the left part. So m dot in minus m dot out, so this is in x direction, so you have to find out the in x direction. So this x direction I can write this one as, so this is m dot x, this is the mass in x direction, minus the mass out is m dot x plus this is dm dot x by dx into dx. So if you write, this one is coming out to be minus dm dot x by dx into dx. So this is equation, suppose this is equation A, I am writing this is equation A. So now I have to find out this m dot x. So m dot x I can write, this is already a mass flow rate, I told you, this is rho into q, or this q, or can write this is area into velocity in x direction, this is velocity in x direction is u. Okay, so now suppose this is my the cube, the small elemental part in which the, suppose this is my small elemental part in which the water is flowing. So this is my small elemental part, and suppose this is my m dot x, this is my m dot in x direction. So this is m dot x, and this is my m dot x plus dm dot x by dx into dx, and this is my dx part, and this is my dz, and this is my dy, this, and this is dx, the cross sectional area of this water flowing, this one cross sectional area. So this is how, this is dz, so this is dz, and this one will be dy. So I can write down this one as rho into area is dy into this is dz into this is u. Okay, so now if you put this one in equation way, suppose you put this one in equation A, so this is coming out to be minus dou by dou x into rho into dx, you come to make this side, this is dy, and this is dz into this is u. So dx, dy, dz is the volume of the system in which the liquid is flowing. So dv I can write down this one dx into dy into this is dz. So now I can put this one, so this is coming out to be minus dou by dou x into rho into dv into u. So this is m dot in minus m dot out, so this is in x direction, this is in x direction. So this is equation 1, so this is equation 1. Okay, similarly if you want to write the rate of mass in minus rate of mass out, so in y direction, so this is in y direction, that is coming out to be minus dou by dou y into rho into dv into velocity in y direction. This is equation 2. Similarly, this is, if you write this one, rate of mass in minus rate of mass out in z direction. z direction, this is coming out to minus dou by dou z into rho into this is d into this velocity in by direction equation 3. Now if you want to find out this m dot in minus m dot out will be equal to, so this is equation 1 plus equation 2 plus equation 3. Okay, so if you add this one, it is coming out to be, if you add this one, is coming out to be minus dou by dou x into rho into u plus dou by dou y rho into v plus dou by dou z into rho into w. So this is my equation 4. Okay, now you have to find out the mass stored. What is the rate of mass stored? Okay, so into this is dV, sorry, this is into dV. Okay, so now you have to find out what is the mass stored. So this mass, rate of mass stored, so there's a mass stored will be equal, I can write this is the, what is the mass stored with respect to time, what is the change in mass stored with respect to time, this is mass flow rate. Okay, what is the mass stored with respect to time? So I can write this mass, we can write this is dou by dou t, this mass can write in this is density into the change in, or this is the volume of the system, density into the volume of the system in which the liquid is flowing. So this volume is fixed, this volume is fixed, it will not change, but density can change. Okay, density of the fluid, it can change with respect to time. So I can take dV as constant and I can rewrite this is d rho by dt into dV. So this is equation 5. Now from this equation and 4, 5, so I will write this conservation of mass equation. This is mass stored in minus mass stored out will be equal to mass. This is the rate of mass in minus rate of mass out. It is the rate of mass stored. If you put this equation 4 value here, that is coming out to be minus dou by dou x into rho into u plus this is dou by dou y rho into v plus this is dou by dou z into rho into w into dv will be equal to d rho by dt into dv. So dv gone. If you write the final equation, this is d rho by dt plus this is dou by dou x into this is rho into u plus this is dou by dou y rho into v plus this is dou by dou z rho into w. Okay, so this will equal to 0. So this is my continuity equation. This is my continuity equation. So this is my continuity equation. Okay, so if you ask me why I am not taking this rho to this d rho by dx, because this density is also changing. Okay, so density is also changing, so this I cannot write this one as rho by rho x. If this will be a incompressible fluid, then I can take this as constant. So this is a general, equation, the general equation of continuity. So this is general equation of continuity. So now suppose I am taking the first case. So this is case A. So if you write down, this is for steady flow. So for steady flow, if you write, so for steady flow, this the property of the fluid will not change with respect to time. This is du by dt will be equal to 0. And the density is not a function of time. Okay, so this is density is not a function of time, but the density is a function of space coordinate. It may be a function of space coordinate, but it is not changing with respect to time. So I can put this one as 0. So I can rewrite this continuity equation dou by dou x. So I cannot take into this side because density is not changing with respect to time, but it may change with respect to space. So I can this is rho u plus, so this is d by dy into rho into v plus this is d by dou z into rho into w will be equal to 0. So this is the continuity equation for steady, and this is incompressible flow. I can write down this is steady and this is compressible. Density is changing. This is compressible flow. Okay, so for steady and compressible flow, this is the continuity equation. So if you want to write down the second case, if you want to write down the second case, okay, if you want to write down the second case, so I'm writing here. So if you want to write down the second case, here I am writing down. So this is second case B. So second case B, if you want to write down, so this is for steady and incompressible flow. So if you want to, this is for steady and incompressible flow. So for steady and incompressible flow, if you write, density is constant. Density is constant. It is not changing with respect to space or time. Means I can, the density is not a function of, it is not a function of x, y, z and t. So here I can write down steady means this is 0, so density is also constant, so I can take it out and it is cancelled. So this is the du by dx plus this is dv by dy plus this is dw by dz will be equal to 0. So this is the equation of continuity for steady and incompressible flow. Okay, so if you want to write down this equation for two-dimensional case, so steady and incompressible equation for this is two-dimensional flow. So for two-dimensional flow, I can write down this W component will become, and this equation is for three-dimensional flow. This is for three-dimensional flow. If you write the two-dimensional, that is dou by dou x. So this is dou v by dou y will be equal to 0. This is for two-dimensional flow. Okay. So now, if you want to derive the one-dimensional continuity equation for steady flow, so we will derive this equation from this basic conservation of mass. So this is rate of mass in minus rate of mass out. This is the basic equation from which we derive this continuity. This is the rate of mass stored. Okay, so this is the basic equation of conservation of mass equation from which we will derive. Suppose this is my system, or this is my pipe in which some water, there is some mass is flowing in this direction. So this is m dot x in x direction, and there is some mass is out of this one. And suppose this is my dx. This is my dx. This is only one dimension. Okay, so I can write this is m dot x plus dm dot x by dx into dx. Okay, this is the component. So if I want to find out the m dot in, so this is m dot in. Okay, this is m dot in. So this is m dot in, and this is m dot out. This is the mass is, whatever the mass will be remaining, that will be stored in this system. So this is m dot in minus this m dot out. So if you write, this is coming out to be, so m dot x minus m dot x plus dm dot x by dx into dx. So this is coming out to be minus dm dot x by dx into dx. So this is equation 1. Okay, this is equation 1. So if you write what is the mass stored, okay, so what is the mass stored? So the mass stored will be equal to same. This is dm dot x, or this is dm dot what is the mass stored in per time. So this can be written as rho into dv. This is the mass stored per time, and the this volume is constant. Okay, this volume is not actually changing. Only density is a function of time. Density is changing with respect to time. So this is this is d rho by dt into dv, and this is equation 2. This is equation 2. But here I have written this is one-dimensional continuity equation for steady flow, and for steady flow this d rho by dt will be equal to 0. So I can write for steady flow, this d rho by dt will be equal to 0. So if you this one, now if you use the conservation of mass equation, so this is m dot in minus m dot out will be equal to what is the m dot stored. What is the m dot stored? So this is already we have find out, this is coming out to be d m dot x divided by dx dou x into dx will be equal to, this is already we find out, this is d rho by dt into dv. So this is coming out to be 0. Okay, so this is coming out to 0 and the final equation is coming out to be d dot x by dou x into dx will be equal to 0, or you can write down this one as dou m dot x by dou x will be equal to 0. Now if you integrate this one, this is coming out to be m dot x will be equal to okay, this m dot x will be equal to what? This is coming out to be equal to constant. This is constant. So what is m dot x? This is will be equal to rho into a into u. Okay, so this is equal to constant. Okay, constant. Okay, so u, as I told you, this velocity field, if you write, this is u I cap plus v j cap plus w k cap. So this is a one dimensional flow, so I can write this is a u, so v can I write that equal to u, so this will be equal to rho a v will be equal to, this is constant. So this is the continuity equation for one dimensional and steady flow. So this equation is generally called, this is for one dimensional and steady flow. Remember this one dimensional and steady flow, the continuity equation we can write, this is rho a v will be equal to constant. Okay, constant. So how we can use this continuity equation? Suppose this is one pipe. Okay, this is one pipe and in which the water is flowing. And if you want to use this continuity equation between two sections, so this is section 1, this is 1 and this is section 2. So you can use this continuity equation will be equal to rho 1 a1 b1 will be equal to rho 2 a2 b2. Okay, this is the continuity equation we can use in the pipe flow. Okay, so this equation is valid for both compressible and incompressible flow. Okay, means this equation generally is if you write down this equation, if you this is rho b is constant, so this equation is valid. So this equation is valid for both this is compressible and incompressible flow. Okay, now suppose for incompressible flow I can write, so this is for incompressible flow. So for incompressible flow, so I can write down this density will be equal to constant. So density will be constant means this can I write rho 1 will be equal to rho 2 will be equal to constant. Okay, so now if you use this one, this will be coming to this a1 v1 will be equal to a2 v2. So this equation is generally used, or I can this one I can write this is ab will be equal to constant. ab will be equal to constant. So this equation generally used when the flow is one dimensional, steady and incompressible flow. So this can be used one dimensional, steady and this is incompressible flow. So this is the basic part we should remember for this continuity equation. Okay, so first we derived the general equation of the continuity equation, then we discussed the different cases for steady flow rate condition and for incompressible flow. Then we gone to for one dimensional steady flow, one dimensional steady flow continuity equation, we derived that one, that is coming to a rho a b will be equal to constant, and we have seen how we can use this equation at different section. Okay, means whatever the mass is flowing at section 1, same mass will be flow at section 2, because mass can neither be created nor be destroyed. So for incompressible flow, we can write the continuity equation equal to A1 V1 and A2 V2. So thank you for watching this video. Thank you all. Thank you.